Hi and welcome back. Today we're going to look at section 4.4, which is more curve sketching, but today it's on rational functions. So we're basically going to do all of the same strategies we did to graph polynomial functions, but for rational functions we also need to look at the domain, figure out what's not included, and also what are called asymptotic behaviors. Most rational functions have vertical and horizontal asymptotes, so that just helps us again gauge how to graph these functions. So we've already looked at, well, we already should know how to find asymptotes, but we're going to begin our lesson on that just to kind of review how to find them. And then we're going to look at a function that's a rational function and go through the steps like we did in section 4.3 on how to figure out all of the parts of the graph and then graph it. Okay? So today our definitions, again, a lot of these things we've already done, but just go through this with you guys so you have them here. So today we're going to look at rational functions. And a rational function is basically a polynomial divided by another polynomial. And the problem with rational functions is that we're always going to have numbers that have to come out of the domain because the denominator cannot equal 0. Okay, so we'll go through that. An asymptote is a line that a curve approaches or gets close to, okay? So that has to deal with limits, so we'll talk about that as well. All right, now vertical asymptotes. Vertical asymptotes are always of the form x equals a, and they occur where the denominator equals 0, but not the numerator. It is possible for rational functions to have more than one vertical asymptote. Doesn't always, but sometimes it might. To find the vertical asymptotes, you just have to simplify the rational function first, which means factor it, and then set the denominators equal to 0 and solve for x. Okay, but remember, it's the factors that are not in the numerator. So we'll talk about that in a minute as well. All right, horizontal asymptotes. They're always written y equals. So you guys got to remember, vertical asymptotes are your x equals equations. Horizontal asymptotes are the y equals equations. Okay? All right, and they occur where the limits of f of x as x goes to infinity or negative infinity equals b. We're going to talk about how we found those earlier, so hopefully this will just be a quick review. If you remember, we did the top heavy, the bottom heavy, or the equal degrees. Those were the horizontal asymptotes. So we're going to go through those on this next page. Okay? All right, and then we have what are called oblique asymptotes. Okay, those are, a lot of you learned those as slant asymptotes. We call them oblique. They're of the form y equals mx plus b, and they occur when the numerator is a degree larger than the denominator. So to find the oblique asymptote, we have to divide. And we're going to use synthetic division typically. It's a lot easier than long division. You can use long division. Either is fine to find that function. All right, and number 7 says a rational function can have at most one horizontal asymptote. So you can have more than one vertical, but only one horizontal. Okay? All right, so let's go through finding vertical and horizontal asymptotes so that you guys are sure you remember how to do this for graphing purposes. All right, so number 1 asks you to find vertical asymptotes, horizontal asymptotes, and oblique. Now, you're either going to get one or the other of these, okay? You either will have a horizontal or oblique. You will never have both. You'll have horizontal asymptotes if the function is either bottom heavy, we went through this last time, or equal degrees, okay? So bottom heavy means the degree in the bottom is bigger. Equal degrees means the degree in the top and the bottom are the same. Those will be your horizontal. You would only have an oblique asymptote if your function is top heavy. Okay, so you will only have one of these two, never both. These are separate, okay? All right, so let's remember how to do this. So we always have to factor. Always, always, always we need to see what the factors are. Again, with me, I don't like these negative signs. So first thing I'm going to do is factor out a negative. The top will become x plus 1. And if I factor out a negative in the bottom, I get 3x squared minus 13x plus 4. Just changes the signs, right? You're factoring out a negative 1. So that negative is like a -1. I just don't have to put a 1 there. So basically you're dividing everything by -1. Now the bottom here can be factored some more. So top is good. The bottom, however, I believe we can factor that. So thing is, we want to always see about common factors. So that's what I'm doing here. If I don't factor it, then I don't know if the bottom has an x plus 1 in it. I don't think it will, but let's see. So we need a 3x squared. So in the first, I got to have 3x times x. And then 4, I'm either going to use 4 times 1 or 2 times 2. But I got to get 13 in the middle. So I'm going to use 4 here because 3 times 4 is 12. And I'm going to put a 1 here. So the last terms, 4 times 1 will give me 4. But when I do the outer 12 and the inner 1, 12 and 1 is 13. So that's what I need. Both these are going to be minus because I need a positive 4. Negative times a negative is positive. But I need a negative 13 in the middle. So that gives me the negative 13. All right, so yeah, none of my factors are the same. So that's good. All right, so let's start with vertical asymptotes. To find vertical asymptotes, you set the denominators equal to 0 and solve. Okay, so vertical asymptotes, set denominators equal to 0. Factors, denominator factors equal to 0. Now, if there was an x minus 4 in the top, then that would not be a vertical asymptote. Okay, remember up here, vertical asymptotes occur where the denominator is 0 and the numerator is not 0. That basically means they don't have the same factor. Okay, so as long as the factors are not in the numerator, okay, I'll say that again, as long as these denominator factors are not part of the numerator, then they are vertical asymptotes. If they are in the numerator, they are not vertical asymptotes. Okay? All right, so let's set those equal to 0. So we got 3x minus 1 equals 0 and x minus 4 equals 0. Solve those. So we get 3x equals 1. X is 1/3. And over here we get x equals 4. Those are your vertical asymptotes. Okay? Solve the denominators. Now, to do the horizontal or oblique, remember you can get one or the other, you look at the degrees. The degree in the top is 1, x to the first. That's the highest power in the numerator. The highest power in the denominator is x squared. Okay? So the denominator has the highest power, so that means that is bottom heavy. That means the bottom is bigger, right? Heavy. So it's bigger in the bottom. So that means it has a horizontal asymptote. When you have bottom heavy, okay, for bottom heavy, your horizontal asymptote is always y equals 0. Okay, always. You don't have to do anything. So as soon as you see the degree in the bottom is bigger, you know that you have a horizontal asymptote and it is y equals 0. Okay. All right, so that's it for that. Okay, let's look at B. Okay, first thing we're going to do is factor. Top doesn't have anything that needs to be done. The bottom I can factor out of 9. Leaves me x minus 1. All right, so vertical asymptotes. We set the denominators equal to 0 and solve. Only for x, remember. 9 is a constant. It's not an x term. Doesn't count. Only the x terms get set equal to 0. Remember, you're solving for x. So we're going to take x minus 1 equal to 0. Solve that, we get x equals 1. So there's your vertical asymptote. All right, your horizontal asymptote. Look at your degrees this time. We've got x to the first in the top and x to the first in the bottom. So these are equal degrees. So for equal degree problems, okay, The horizontal asymptote is always the leading coefficient divided by the leading coefficient. You guys got to write that out if you want to. Okay? Leading coefficient divided by leading coefficient. Leading coefficient is the number in front of that highest power. So for this problem, it would be 4 over 9. So your horizontal asymptote is y equals 4/9. Okay? So neither one of part A and B have an oblique asymptote because they had horizontal asymptotes. Okay? So for bottom heavy, that's the easy ones. Y equals 0. For equal degrees, it's pretty much just as easy. You take the leading coefficients and make a fraction out of them and reduce them. Okay? Make sure you reduce it if you can. All right, so the last one I'm sure in part C is top heavy, which it is, right? The degree in the top is bigger. So this one will have an oblique asymptote and not horizontal asymptote. Okay, so we got to see if we can factor. So the top 2x. All right, so to get 2x, we need 2x times x. And the only way to get 3 is 1 times 3. So I just got to figure out where to put the 1 and the 3. So I want the 1 here and the 3 here because I need 1 in the middle. Okay, otherwise I wouldn't get that. So when you do the outer and the inner, 3x minus 2x is that 1x in the middle. And we need a negative 3, positive 1. Okay, however you guys remember factoring, that's fine. It's the way I kind of showed everybody, but and then at the bottom I'm going to factor out that negative side. Okay, so again, none of these are the same. So that means this is your vertical asymptote. And then our oblique asymptote, we're going to have to divide this into this. Okay, so the vertical asymptote, any factor in the bottom, set that equal to 0 and solve. So we get x equals negative 3. So that's your vertical asymptote. Now this one has an oblique asymptote. Okay, you can say OA. As long as you remember what that is. Okay? Instead of HA, it's an OA, oblique asymptote. Now, we're going to divide. Okay, so I'm going to do synthetic division. So remember, you solve for the bottom, which we already did. That goes in the box. And then I'm going to put this coefficients out here. So 2, negative 1, negative 3. Now you can do long division. Most of you guys do not like long division, but you could do long division. Okay, I'm just doing synthetic because we don't do this very much and this is much quicker. So let me remind you, you solve for the bottom, which we already did. That number goes in the box, and then the coefficients 2, negative 1, and negative 3 go on top. And then you leave a space, and then you drop down that first coefficient. That's how you set up synthetic division. Then remember, you just take whatever's in the bottom and multiply it by what's in the box. So negative 3 times 2 is negative 6. You put the number here, and then you add this column, which is negative 7. And then you do the process again. Negative 7 times negative 3, positive 21. Add this column, you get 18. The last number is the remainder, and we do not need that for the oblique asymptote. These are the, remember the oblique asymptote is y equals mx plus b, right? So this is your m, and this is your b. It's always going to be that way. So we get y equals 2x minus 7. And that is your oblique asymptote for top-heavy problems. So top-heavy problems do not have a horizontal asymptote. Okay? All right. So remember, if you divide, you don't need the remainder. Oblique asymptote is just this part of this. So just the two numbers out front. All right. Moving on to number 2. Now we're going to do our function like we did in polynomials, go through all of the stuff we need to be able to sketch this graph. So where's the function increasing, decreasing? Where's it concave up, concave down? Are there any other points we have? And so forth. Okay? So remember, to start, we have to find where the function is increasing and decreasing, which is the first derivative. Now, in section 4.3, we found the first and second derivative first because it was a polynomial. However, since this is a quotient rule, we need to do a little work and we're going to have to simplify it because we have to find the second derivative. So that's why we're going to just do this first, okay? You could do the first and second right away. That's fine, but just this way this problem is set up. We're going to just find the first derivative and do our increasing and decreasing step. All right, so to find the derivative using the quotient rule, we start with the bottom times the derivative of the top. So the bottom times the derivative of the top, the derivative of x minus 3 is just 1, minus the top, x minus 3, times the derivative of the bottom. Derivative of 4x is 4, derivative of that is 0. So the derivative of the bottom is 4, all over the bottom squared. Okay? Now, since we have to use this, we need to simplify it. So, let's see what we get in the top. 1 times 4x plus 12 is just 4x plus 12. Now, we got a minus sign there. So think about that 4 out here. So we're going to do 4 times x, which is 4x, but it's minus. And then we got 4 times negative 3, which is negative 12, but minus the negative 12, so that's plus 12. All over the bottom squared. All right, so that means the first derivative, if we simplify this, 4x minus 4x is 0, and 12 plus 12 is 24 over 4x plus 12 squared. That's our first derivative, plus 12 squared. Okay, so how do we find increasing and decreasing? We set this equal to 0. Okay, so we're going to take that function, I'll put it here, 24 over 4x plus 12 squared, set it equal to 0. All right, so we got to remember what happens when we have no variable up here. Always when you have a fraction, whatever's in the bottom is going to go away because you can multiply this times 0. Remember, we're cross multiplying. Okay, so 4x plus 12 squared times 0 is 0. So we're going to end up with 24 equals 0, which is not true. Okay, so that just means there are no critical values. Okay, so our first derivative gave us we have no x. The only x's we would solve for are up here. However, let's go back and talk about this function and talk about the domain. Okay, remember in a rational function, the denominator cannot equal 0. And if the denominator cannot equal 0, then x, if I solve this for x, if 4x can't equal negative 12, then x cannot equal negative 3, right? That number is not in the domain. I can't use negative 3 anywhere in these intervals, anywhere in this problem. I cannot use negative 3. Okay? So that means even though there's no critical values on my first derivative, I still have to take out negative 3 because that is not in the domain. Right? I can't use that. So I still need to make sure what's going on both sides of this function. However, when I look at this, because this is what I'm going to plug it into to test, my test points, whatever I put in the bottom and I square it, this bottom is always going to be positive, right? I don't care if x is a positive or negative number, smaller or less than negative 3. Whatever I get in here, if it's positive or negative, when you square it, it's going to become positive. And the top is always positive. So you're always dividing a positive number times a positive number, no matter what. So I know both of these sides are positive. So all that means is my graph is increasing everywhere. Okay? I still have to test. If I didn't have a domain issue, then I would have just had a number line of all real numbers. But I do have to test that. So where is my function increasing? This is why I'm telling you that. So f of x is increasing. You can't say from negative infinity to infinity because you can't use negative 3. So we have to say from negative infinity to negative 3, and then -3 to +50. Not because that's a critical number, but because it's not part of the domain. Okay, so that's different. So we didn't get any critical values, not at least for the first derivative. All right, so f of x is not decreasing anywhere, right? However you want to say that. It isn't decreasing, okay? So it's increasing everywhere. All right, so we know that about the graph when we graph it. So it's either concave up, increasing that way, or if it's concave down, it would be increasing like that, right? So there's only two possibilities for this graph right now. So now we're going to see is it concave up or concave down based on the second derivative, okay? All right, so remember your first derivative. We need that because we got to take the second derivative. So I'm going to write that down on the next page for our concavity. Okay, so let's remember the first derivative was 24 over 4x plus 12 squared. And then we got to take the second derivative. Okay. Let's talk about local max and local mins. So I don't have to keep coming back to this page. So there were no critical values, no change here, so there were no max or min. So this graph does not have a max or min based on the first derivative. So I'm going to go ahead and write that in part C, so I don't have to keep flipping back to the next page. So there is no local max or min, right? Because there was no critical values. Okay. Now, inflection points, I'm not sure yet. There may or may not be. We just have to wait and see. Okay. Now, when we do the concavity, okay, same thing. I still have to remember that x can't be -3, right? So that has to be part of my number line. I have to take that out of everything because it's not in the domain. All right, so now we got to find the second derivative. Second derivative. And then that's what we got to set equal to 0. All right, so we're going to start with the bottom. Quotient rule again. Bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom. This is a chain rule. So we're going to bring the 2 out front, subtract 1, leave the inside alone. So 2 times 4x plus 12 to the first power, then times the derivative of the inside, which is 4. All over the bottom squared. So if you square a square, you get a fourth. But I'll go ahead and write it squared just so you can see that, right? The bottom square. Okay, so now let's clean that up a little bit. All right, so in the top, this is 0. 0 times anything is 0. So over here, let's fix this. 24 times 2 times 4. 24 times 2 times 4. 1 negative 192, right? 4x plus 12 over 4x plus 12 to the 4th squared. Okay? All right. So now if we're going to do test points, so we got to set this equal to 0 and solve. Okay? All right, so we're going to take negative 192, 4x plus 12. I'm not going to multiply it out. You'll see why in a minute. Over 4x plus 12 to the 4th. Okay? All right. Well, I guess I could have done this here. So I got 1 here and 1 here. So if I reduce that by 1, that becomes 3 of them down here, and that goes away. So I got negative 192 over 4x plus 12 to the third power. That's what I'm going to set equal to 0. Okay? So in the same respect as last time, if I multiply, this goes away, and I'm just left with negative 192 equals 0, which is not true. So again, no hypercritical values. But when I do my test points on the second derivative, I still can't use negative 3. Okay, so I need to test what's going on each side over here. Okay? All right, so now I do need some test points because anything cubed, that could be positive or negative. So I need something to the left of negative 3, let's say negative 4, and something to the right of negative 3, 0. Okay? All right, so let's look at the bottom. I know the top's always negative. So the bottom, if I use negative 4, that's going to be negative 16 plus 12. This is going to be a negative number, and when I cube a negative number, it is negative. So a negative divided by negative, positive. So this side should be concave up. If I put 0 in here, this is 12, right? 0 plus 12. 12 cubed is positive. So now I got a negative over a positive, which is negative. So this side better be concave down. All right, so even though I didn't have a hypercritical value, I do have a break in concavity. So this question asks me, where is my function concave up and concave down? So f of x is concave up on this side. So from negative infinity to negative 3. And f of x is concave down on the right side between negative 3 and positive infinity. Right? All right, so we got that done. Okay, so do we have any inflection points? Well, if this was a point in my domain, yes, I guess it would be. But remember, it's not a hypercritical value. That's the point we could not ever use. So that's not a point of inflection. Okay, that's an asymptote. We can't use it. So there is no inflection point. So some of you might say, why? That changed signs. Yeah, but that was not a hypercritical value. It was the number we took out of the domain. Only hypercritical values could be possible inflection points, okay? So we don't have any inflection points either. This is a boring graph, okay? None of those things. All right, so now we're finally down to part D, which is the asymptotes. So we need the asymptotes. So that's the original function. Let me write that down. Here's the original function. X minus 3 over 4x plus 12. Okay, that was the original function. So vertical asymptotes, set this equal to 0 and solve. So 4x plus 12 equals 0. 4x equals negative 12 when you move that over. X is negative 3. That's your vertical asymptote. That's why we can't use it. It's an asymptote. Remember, that's the number we took out of the domain. Horizontal asymptote. Is this top heavy, bottom heavy, or equal? Okay, the degrees are the same next to the first. So this is equal degree. So that means the leading equal degree. So we need the leading coefficient over the leading coefficient. So that would be 1 over 4. So your horizontal asymptote is 1 over 4. 1/4. Okay? All right. We're getting there. Got a lot of information here. All right. Lastly, find any x or y intercepts. So again, let me write the function down since we're on a new page. Let me remind you how to find the x and y intercepts. Okay. The x-intercepts, okay, x-intercepts are what makes the numerator equal to 0. So x-intercept, what makes the numerator equal to 0. Okay, that's how you find your x-intercepts. So we would take x minus 3, set it equal to 0, and get x equals 3. So that's your x-intercept, 3, 0, where it crosses the x-axis. Okay, so we always set the numerators equal to 0 to find those. You can also let y be 0. Well, if you guys remember let y be 0, you can do it that way. That's perfectly fine. So you'll get the same answers. This is just a little shortcut. All right, for y-intercept, okay, yes, you let x be 0, but if you let x be 0, you're going to end up with the constant divided by the constant. So the y-intercept is the constant term divided by the constant term. Think about that. If you're letting x be 0, all the terms with x in them are gone. They're 0. So you're just left with the constants. So our y-intercept would be negative 3 over 12, which is negative 1/4. So your y-intercept is 0, negative 1/4. Okay? All right. So those are 2 points on the graph that I know. So 3, 0, and 0, negative 1/4, which is a little close to there. Probably not there, but okay. So there's my x and my y-intercept. Now, remember your asymptotes. Vertical asymptote was at negative 3. Horizontal is at 1/4. So vertical at negative 3 goes this way. It's vertical asymptote. Always use dotted lines for asymptotes. So they're not really part of the graph, but you can just see them this way. And then negative 1/4. Oh, positive 1/4, right? So up here, horizontal. Can't get real close to 1/4, but looks like almost a half. But you get the picture. We're just sketching, so as close as you can be. So 1/4. Okay, so now that's the horizontal asymptote was positive 1/4. The y-intercept was at negative 1/4. Okay, so we know that rational functions always look, they have curves. They kind of look like that. So we can kind of see here this side, and they always get close to the asymptotes. So I don't really need to do much here. I could find another point over here if I want, maybe at negative 2. And then I need to know where the other side of the graph is. Typically, if it's just a regular rational function, they're going to alternate, but it could be in one of the other quadrants. So at this point, since we don't have enough, I would say let's just go get some other points on the calculator. So go to y equals, put in your basic main function, f of x, make sure the numerator's in parentheses divided by the denominator in parentheses. Again, if you have the new version, it already gives you a fraction, and that's fine. You can put in the fraction first, then you don't need the parentheses. Okay? So I'm going to go to the table, and I'm going to look at where's negative 2. Okay, just so I can see. So negative 2 is at negative 1.25. Negative 1.25 is about here. Okay. Now, negative 3 is an error because that's the asymptote. So I know this side of the graph. I'm going to get really close to that. Go through there, and then it's going to get really close to that. Remember, there's limits. Okay? So that's what that side looks like. Now, I just need some points over here. So that's it. Let's look at negative 4, which is 1.75. 1.75 about here. Negative 5 is at 1. And negative 6. Okay, so I can kind of see this side is going to go like that. Right? Now, I didn't really need the concavity, but let's kind of talk about that. On the left side of negative 3, let's do the increasing and decreasing. Remember, the whole graph was increasing, right? So on both sides of this, we were increasing. Okay. Then for concavity, the left side was concave up, the right, looking at the wrong page today. Sorry about that. So on our graph, the left side was concave up, the right side was concave down. So this should be that way, and this should be that way. So if I couldn't already see the way this graph was going based on those points, I knew that I have concave up increasing, which is that. That's concave up and increasing. And on this side, we're increasing, but concave down, which is that shape, right? So you can still do the shapes, we can still do the boundaries, but typically for rational functions, as soon as you have a couple points, you automatically can see the way that curve is going to go. So, you know, use what you need to, okay? But it did check out. This is definitely increasing everywhere. Pen's going up everywhere. And this side's definitely concave up, and this side's definitely concave down. Okay? All right. So that does it for the rational functions. So you guys can work on homework. Let me know if you need anything, and if not, I'll see you back here next time.